Fire. It can cook our food or, well, destroy our homes. It's one of the most powerful forces in nature. But have you ever stopped to think about what fire is, really? Today, we're going to break down the science of it, from that very first spark all the way to the final ember. Let's dive in.
You know, this one little question kind of changes everything. We see flames, right? And we think of fire as a thing you can point to, but you can't actually hold it. That's because fire is a high-speed event. It's a chemical reaction that's happening right in front of our eyes. And once you start seeing it that way, as a process, you start to get a handle on its true power.
So if fire is a process, then it has to have a recipe, right? And it turns out, yeah, it does. It needs a few key ingredients to come together in just the right way for the magic to happen.
Okay, so here's the official scientific definition. At its core, you've got a fuel source. It combines with an oxidizer, which is usually just the oxygen in the air, and then it needs a little kick of energy, heat, to get the party started. Simple enough, but there's one more piece to this puzzle. This is it. This is the whole shebang, the fire tetrahedron. It shows the four things fire absolutely cannot live without. You need fuel to burn, heat to get it started, and oxygen to feed it. But that fourth side, the chemical chain reaction, that's the secret sauce. It's what makes the process self-sustaining. The fire creates its own heat, which keeps the reaction going and going and going. You take away any one of these four things, and the whole structure just collapses. Poof, the fire's out.
So, once a fire has its four ingredients, it doesn't just sit there politely. No, it wants to grow. It wants to spread. And the way it does that is by moving its most critical ingredient, heat, from one place to another.
And it turns out it has exactly 3 ways of doing this. Each one works a little differently, and if you can understand them, you can start to predict how a fire is going to behave.
So here they are, the 3 ways heat gets around. First, you've got conduction. That's heat moving through direct touch, like when you leave a metal poker in the fire and the handle gets hot. Then there's convection, which is heat moving through hot gases and liquids. This is a big one. It's why smoke rises and how fire spreads upwards so incredibly fast in a building. And finally, you have radiation. This is the spooky one. It's heat traveling as invisible waves. It's why you can feel the warmth of a bonfire even from across the yard, and it's how a fire can set something else on fire without ever even touching it.
All right, so we know what fire needs and how it spreads its heat. But what is actually happening on a molecular level when, say, a log starts to burn? It's not just one thing, it's a whole sequence of events.
So let's watch a log burn in slow motion. First, it just heats up, right? It's absorbing energy. Then the really critical step happens, pyrolysis. This is a fancy word for the heat getting so intense that it literally breaks down the solid wood and forces it to release flammable gases. Now get this, it's those gases that are actually burning, not the solid wood itself. Once those gases ignite, boom, you get sustained combustion, and that chemical chain reaction we talked about takes over.
Now, when we're talking about ignition, there are 2 super important temperatures you gotta know. The flash point is the minimum temperature where a fuel is giving off enough flammable vapor that it could catch fire if a spark came along. But the auto-ignition temperature, that's way more dramatic. That's when something gets so hot it just bursts into flames all by itself. No spark needed. So the big difference is just that, whether you need an outside spark or not.
Okay, the heat and the flames are what we see. They're what we're scared of. But a lot of the time, they aren't even the most dangerous part of a fire. That chemical process of burning creates this nasty cocktail of byproducts that are often invisible.
Yeah, what a fire breathes out can be just as deadly as its bite. Smoke, obviously, it blinds you. Soot messes up your lungs, but the gases, they are the real silent killers. Carbon monoxide is the famous one. It's toxic, you can't see it, you can't smell it. But just think about what's in a modern house, plastics, foams, all sorts of chemicals. When that stuff burns, it can release a whole toxic soup of poisons into the air.
All right, now for the most important part. Because if we understand fire's recipe, we also understand how to unmake it. Every single method of fighting a fire is designed to do just one thing, to break that tetrahedron. And this slide just lays out the whole strategy perfectly. To kill a fire, you just have to break one of the 4 sides of that tetrahedron. You can cool it with water to take away the heat. You can smother it with something like foam or carbon dioxide to cut off the oxygen. You can remove the fuel, which is what firefighters are doing when they clear a fire break in a forest. Or, and this is the really clever one, you can use special chemicals to directly attack and stop that chain reaction itself.
This says it all, doesn't it? Fighting fire isn't just about spraying a bunch of water.
It's applied chemistry. It's applied physics. It's about strategically taking apart the process by ripping away a component that it absolutely cannot survive without.
You know, understanding all this science isn't just for firefighters. It actually influences how we build our homes, the kinds of materials we use, how we design our safety systems. So the real question becomes, with this knowledge of how fire's born, how it moves, and how it dies, how can we get better at engineering our world to keep it from ever starting in the first place?